Okay, this is an actual test from a few years back, so we're going to fire through this one. First part's knowledge here, so let's take a look. Radioactive substance has a half-life of 15 days. How much of the original 64 grams will be left after 75 days? Let's start off with this. 75 divided by 15 is 5, which means that's 5 cycles. And with a half-life, every cycle you chop it in half. So without even using any formulas, it's a knowledge question. So we'll go 64. I'll chop that in half to 32. That's 1 cycle. Chop it in half again. That's another cycle. Chop it in half again. That's another cycle. Chop it half again. That's another cycle. That's 1, 2, 3, 4 cycles. We got to go one more time. That'll be 2 grams. So that's the answer for that one. 2 grams left over. Basically, you chop it every 15 days. You chop it in half. So this was 15, 15, 15, 15. The last 15 days there gives me a total of 75 days. We're at 2 grams. Okay, 200 gram arrow shot out of the bow. Chooses 200 newtons of force over a distance. So this is just work. The force is 200. Let's see, 200 newtons, and the distance is 0.5, which is 100 joules of energy. Okay, then it says, the arrow leaves the bow at 30 meters per second. Find the kinetic energy. Okay, EK. So the mass, oh, it's in grams. 2 kilograms is going 30 meters per second. That's fine, so 30 squared times 0.2 divided by 2 is 90 joules. So I stretched the bow back with 100 joules of energy, flung the bow out, the arrow shoots out with 90 joules of energy. It's not 100%. We seem to have lost some energy here. So the percent efficiency is I accomplished 90 joules of energy, but I had to put in 100 joules, and we lost a little bit. Okay, so times 100. I said, where'd the energy go? Somewhere, it's probably heat. Heat in the string, because you're stretching it, or it could be friction of the arrow on the bow. Like maybe it was touching the side, and when it went out, it created some friction on there. All right. How much energy does it take to boil 8.6 kilograms of water at its boiling point? So this is an LV question. I give you both because there's probably different versions in the classroom, but Q equals MLV. If it was to melt, then it would have been the LF one. 8.6 kilograms is 2.3 million. So 2.3 exponent 6 times 8.6. That comes out to, well, let's go scientific. 1.978 times 10 to the 7 joules. All right. These are the good nuclear reactions. Scare people, but they're not really that hard. The top and the bottom just have to add up. We have 12 on the bottom, so the other side of the arrow has to also be 12. There's 11 there, so this one will have a 1 on the bottom. That's a 24, that's a 23, so this will also be a 1. So we're looking for something with a charge of 1 and a mass of 1. That's a proton, which is basically just a hydrogen atom. We got carbon here. The top is 14 is 14, so there's 0 on the top. 6 to 7, there's going to be a minus 1 on the bottom. So which particle is a charge of minus 1 and essentially a mass of 0? That's a good old electron. Or we call it a beta particle. This one we got 55 on the top, 51 here, so this one we're left with a 4 on the top. 4 and 51 make 54, and the 2 on the bottom. That's number 2 on the periodic table, but we also know it as a alpha particle. Okay, that's it for the knowledge part. A 215 kilogram test cart with frictionless wheels is pushed along a track with a 40,000 watt electric motor for 5 seconds. How much work is done on the car? So they didn't give you force times distance, but they tell you the watts. So that's 40,000 joules every second. And it was on for 5 seconds. So we're going to multiply them together. So 40,000 times 5 is 200,000 joules of energy. What's the cart's velocity at the end of the track? So assuming it's frictionless, so this will completely go into kinetic energy. Okay, the energy has to go somewhere. The electric motor did some work. The car is now moving at the end, which means it went into kinetic energy. So let's sub it in here. 215. The velocity, oh, we don't know the velocity. We know EK, it's going to be 200,000. So now we have to solve for V. So 200,000 times 2, divide by 215, and then square root that. 43 meters per second as the velocity. At the end of the track, the car hits a curved ramp and goes straight up into the air. Find the maximum height. So let's draw a picture of this one. So the car goes straight up off this ramp. At the maximum height, the velocity will be 0. All of the energy, okay, it's all of the energy that we got at the beginning turned into EK, then the EK turns into EG. So 200,000 will equal mgh. Mass is 215. Gravity on Earth is 9.8. Just left to find h, so we got 200,000. Divide by 215. Divide by 9.8. H comes out to be ridiculous. 95 meters in the air in your car. Well, it's going to be pretty hard when you come crashing down. Okay, next question. We got a roller coaster. Starts at the top of a hill at 1.5 meters per second and has a speed of 27. Already I see we have the speed, hold on, the speed at the bottom. On the second hill. I was thinking we're going to have everything at the beginning, but so we don't know about the first hill. It's that fast on the first hill, so let's do the relevant picture here. So we got 1.5 meters per second here. The second hill, it's going 27 meters per second, and it's 5 meters above the ground. So that's the key spot that we have for total energy. Here, I don't know the height of the initial height of the roller coaster. I have the speed there. So it's the second part of the question. I can use that to get E total. To give you the mass, so you don't have to assume anything about that. EG is mgh. And the height is 5. EK is mv squared. Now we're going to have to add that up. So 650 times 9.8 times 5 is 31,850 plus, that one is 236,925. Add the two together, we get a total of 268. That's the total amount of energy in that roller coaster everywhere on the ride. The lower you go, the faster you go. The higher you go, you slow down and gain altitude, and then you release it when the weight goes down. So find the initial height. So now we're going to look for the initial height. So E total, EG plus EK. I know E total. It's a fixed thing. It stays the same. 268 EG. So we have, we're looking for the height. So, but it's 650, 9.8 on Earth, and the height plus, oops, that's not supposed to be a plus sign. And we got to find the EK, which will be 650 times the velocity 1.5 squared all over 2. Okay, let's find out what this number is. 650, 1.5 squared, and then divide by 2. That's 731.25, which I'll subtract from that guy, 268. So this comes out to be 268, 043.75. 650 times 9.8, 6,370 times h. Now you just find h, so divide that into the other formula. It's 42.1 meters. In reality, there's always a loss of energy. Where does the loss of energy go in a roller coaster? There'd be friction in the wheels, which would turn into heat, and that would just go off into the rails, I guess, into the air, wherever it wants to go. Okay, substance X, a half-life of 16 days, and it's after a year. Let's see, 365 divided by 16. Let's see, well, this is not a, it's not a knowledge question, it's a thinking question. 22.8125 cycles. Okay, I can't do that in my head because I can't divide it in half 22.8 times. We'll have to use exponents. So if I want to know the amount of stuff that we have now, it's the original amount times a half by the number of cycles. So the time that went by divided by, you can call it T, with a little h for half-life if you want. Okay, but this will be a half-life. We already done that here. I already have the number of cycles, so I can just say, I started with 555 grams of stuff, and I have to multiply it by a half, 28.8125 times. And your calculator will take care of that. If I go 0.5 raised to the power of, a half time, it's like 0.0000, it's really, really small. And then I multiply by 555. I'm going to put that in scientific notation. Okay, that comes out to 7.53 times 10 to the minus 5 grams. Okay. Last page. Niagara Falls has 2,400,000 kilograms of water falling 51 meters every second. How much potential energy is available? So we can look up EG. It's 2.4 million times 9.8 times the height of 51 meters. We might be going back into scientific notation again. 2.4 exponent 6 times 9.8 times 51 is 1.1995, so 1 point, oh, right over now. Joules in a second. Okay, this question says how much would be produced by Niagara Falls for the whole year? So that's joules every second. So we got to figure out how many seconds are in a year. 365 days times 24 hours times 60 seconds times 60 minutes times 60 seconds, so 365. That's 31,536 seconds in a year. Just gotta double check that. 365 times 24 hours times 3,600. Yep, we got it. So then the actual energy would be that guy. 1.1995 times 10 to the 9 times 31,536,000. 1.1995 exponent 9. Multiply by the final. The other answer, it comes out to 3.78 times 10 to the 16 joules. That's what the Niagara Falls produces in a whole year. Now, if we did nuclear power is kind of cool. There's energy equation. E equals mc squared. This is the mass that disappeared or was converted. And this is the energy you get out, and c is the speed of light. So c is 3 times 10 to the 8 meters per second. Sometimes c is heat capacity, but yeah, the letters get confusing sometimes. But let's fill this in. We know the energy. 3.78 times 10 to the 16 equals mass times 3 times 10 to the 8 squared. So we go 3 exponent 8 squared. It's 9 times 10 to the 16. And divide that into the other one, and we get 0.42 kilograms. So that's 420 grams of substance that you can make disappear and will replace Niagara Falls. But nuclear reactors, you don't put in a kilogram control rod, or not control rod, fuel, and take it out with nothing at the end. It's a small percentage that disappears. So you would still need a significant amount of uranium. But let's see, we've got an unknown amount of metal here. There's my metal block. 64 grams. It's heated to 100 degrees Celsius. And it's dropped into a container with 33.6 grams of water at 10 degrees Celsius. So they're going to mix a chunk of metal in here. Final temperature is 15 degrees. And they're being nice to us. Okay, this is going to be the loss size. So negative Q loss equals Q gain. So negative MC delta T. C for the metal is what we're looking for. The temperature, well, let's see, it went from 100 down to 15. I'm pretty sure that's a drop. We can figure it out. 100. It's a drop of 85 degrees. Negative and negative, they'll cancel each other out. This side we have 0.0336 kilograms. 4,200 is the heat capacity for water. And what did the temperature do here? 10 to 15, that's up 5. Okay, so now we just have to figure out the C value. So I'm gonna get that side. .0336, just double check. 4,200 times 5. 705.6, good. So 0.064 times 85 is 5.44, and I'm going to divide that into that number. Maybe I'll fill that in then. 85 is 5.44 C. And divide that out and I finally get the C. Okay, that one's done.